The XenonNT and Panda X direct detection dark matter experiments have just reached a mind-boggling level of sensitivity. Today we will come to understand how these experiments search for dark matter, how their extreme sensitivity now represents a new hurdle in that search, and how scientists can penetrate the neutrino fog to continue to look for the most feebly interacting particles in our universe. It is not always easy to see through the fog. Fog stymies, fog obscures, fog hides. It's easy to see hints of people, objects, fears that may not exist. And it's just as easy to miss something vital. This sentiment carries over into the world of particle physics. If dark matter consists of particles, those particles must interact extremely weakly with matter, and hence our detectors. Otherwise, we would have captured them already. So hunting down dark matter will likely require us to search for particles that interact more weakly than any we have ever observed. That raises a problem. If dark matter triggers our detectors less frequently than other particles, those other particles can swamp the signals produced by dark matter interactions and leave us looking for the proverbial needle in a haystack. And as dark matter search experiments become ever larger and ever more sensitive, the list of particles they can capture expands. This month, two cutting-edge dark matter direct detection experiments, XenonNT and Panda X, reported that they have reached an exquisite level of sensitivity and added an extra hurdle to the search for dark matter. These experiments have captured the scattering of solar neutrinos off the xenon atoms in their detection tanks. The detection of neutrinos is a feat usually reserved for more massive Cherenkov water detectors, such as Super Kamiokande. These results are a massive step forward in the field of direct dark matter detection. Direct detection dark matter experiments have finally become stable enough and sensitive enough to capture neutrinos, particles that penetrate the entire Earth without interacting. However, this realization is bittersweet. Given that we have not found particulate dark matter yet, it must, if it exists, interact even more weakly with our detectors than the solar neutrinos that are streaming through those detectors constantly. That means that these solar neutrinos now represent a new background for direct dark matter searches. They're particles that swamp our detector and cannot be blocked by any viable thickness of shielding. This milestone in direct dark matter detection used to be called the neutrino floor, a hard limit that dark matter physicists would find it very difficult to go beyond. Now, many prefer the term neutrino fog, a challenging, obfuscating barrier that will make our searches lengthier and more difficult, but which can be overcome with the right approaches and the right technology. It appears that if we are to detect dark matter directly, we will need to find ways to peer through the gloom of the neutrino fog. So let's start from the start. What is dark matter, and what exactly are dark matter direct detection experiments looking for? Direct detection dark matter experiments such as XenonNT and Panda X are looking for the very particles that make up dark matter. An overwhelming number of independent observations paint an image of our universe where its evolution is dominated by two key components, the exact natures of which are still widely unknown: dark energy and dark matter. While dark energy appears as an almost uniformly distributed energy density responsible for the accelerating expansion of the universe, dark matter is a new kind of non-luminous matter that is, so far, imperceivable via any interaction except gravity. The existence of dark matter can be inferred from fluctuations in the cosmic microwave background radiation, the cosmic web of structure formation in the universe, and the nature of gravitational lensing observations, galaxy cluster mergers, and galaxy rotation curves, which all point to the existence of additional non-luminous matter. Physicists have come up with many ideas regarding the particles dark matter may consist of. The weakly interacting massive particle, or WIMP, is a class of hypothetical particles that have been the leading candidate for dark matter for decades. The main reason for its popularity is that WIMP models can naturally explain the amount of dark matter observed in our universe. The standard assumption of WIMP production is that WIMPs are thermally produced in the early universe at high temperatures. WIMPs can annihilate with each other into normal particles, and the weak annihilation rate explains the stable amount of dark matter we observe today. If dark matter annihilates, that indicates that it should interact with regular matter in other ways beyond the gravitational, and hence WIMPs can be hunted in matter detectors. The job of direct detection experiments such as XenonNT and Panda-X is to hunt for WIMP dark matter in the parameter space where it's predicted to exist by many beyond standard model theories. But how can we go about capturing these dark matter candidates if they interact so weakly with our detectors? Well, it's devilishly difficult. Direct detection dark matter experiments aim to unambiguously observe interactions between the nuclei of atoms and theorized particles of dark matter. Detectors such as XenonNT and Panda-X exploit the fact that our galaxy appears to be surrounded by a halo of massive dark matter, and if dark matter particles exist, billions of them must be streaming through the Earth and any detector on it every second. Today I will explain the operation of the XenonNT detector, but note that Panda-X operates very similarly. XenonNT is the world's most sensitive WIMP dark matter experiment. The experiment is hosted by the INFN Gran Sasso National Laboratory, located between L'Aquila and Teramo, about 120 kilometers northeast of Rome in central Italy. XenonNT is located 1,400 meters underground to shield the detector from cosmic and other radiation. The thick layer of rock above the laboratory reduces the cosmic ray flux by a factor of 1,000,000, and the neutron flux is about 1,000 times lower than on the surface, due to the very small amounts of uranium and thorium in the dolomite rock of the local mountains. Both are crucial for reducing unwanted particle interactions in our detector that could mimic a dark matter interaction. XenonNT is a huge tank of 8.5 tons of ultra-pure liquid xenon. Cryogenic systems maintain the xenon in liquid form at a constant temperature and pressure for years without interruption, while scientists intently watch for the scattering of a dark matter particle off a xenon atom. Xenon is an incredibly stable, unreactive element. Liquid xenon also has an incredibly high density of about 3 grams per centimeter cubed, 3 times larger than the density of water, and it has a boiling point of 178 Kelvin, or minus 100 centigrade, at low pressures. Theoretical calculations show that the probability of a hypothetical WIMP interacting with a detector nucleus is proportional to the atomic mass of that nucleus. Xenon has a high atomic number of 131, boosting the chances of a WIMP interaction. These characteristics of xenon allow for the construction of stable, compact dark matter detectors with large target masses and simple cryogenic systems. Particle scattering in the liquid xenon, either from the xenon nucleus or its electrons, create both scintillation light and ionization electrons. Xenon is a scintillator. Incoming particles excite the xenon atoms, which then rapidly de-excite with the emission of light at a characteristic wavelength, 175 nanometers. Xenon is transparent to such light, and the wavelength is detectable by commercial photosensors. So when a particle interacts in the XenonNT detection tank, a prompt flash of scintillation light, S1, is captured by photomultiplier tubes at the top and bottom of the tank. However, incoming particles also ionize the xenon atoms, producing free-floating electrons. These electrons drift upwards under the influence of an electric field towards a layer of gaseous xenon, where a stronger electric field extracts them into the gas and produces a secondary flash of light via electroluminescence. The intensity of this secondary flash, S2, is proportional to the number of electrons ionized from the xenon initially. The time delay between the prompt S1 and the delayed S2 light flashes is directly related to the distance the ionized electrons travelled, and thus gives us the depth or Z coordinate of the initial particle interaction within the xenon tank. The X and Y coordinates of the initial interaction are inferred from the distribution of the S2 light on the top array of photomultiplier tubes. Hence, XenonNT can reconstruct the 3D position where a particle interacted within the tank. Determining the 3D position of an interaction is incredibly important. If an interaction appears to have happened near the edge of the tank, it's possible that an atom in the tank structure radioactively decayed, producing a photon or electron that then interacted with the xenon. But due to the high atomic number of xenon, 54, it's actually excellent at stopping low energy photons. This self-shielding capability can be exploited for further background reduction. Hence, when searching for dark matter interactions, it's safer to define a safe fiducial volume of xenon in the centre of the xenon tank, where interactions are less likely to be due to mundane backgrounds. The energy of a particle that interacted in the xenon can be determined from the amount of prompt and secondary light that is released in any interaction. Okay, so it's possible to determine that some kind of particle interacted in the xenon and exactly where in the tank, but how do we determine what kind of particle interacted in the xenon? Because that's going to be very important if we want to track down elusive WIMP dark matter particles. Well, it's possible to separate out different types of particle interactions using the relative amount of light released in the S1 and S2 flashes, the S1 divided by S2 ratio. Most background interactions, such as those with photons and electrons, scatter off the electronic shell of the xenon atom. These are referred to as electronic recoil interactions, or ERs. On the other hand, heavier particles such as WIMPs or neutrons can interact with the nucleus itself, referred to as nuclear recoil interactions, or NRs. Electronic recoils and nuclear recoils create different amounts of prompt and secondary light, allowing the two types of interactions to be identified. When looking for nuclear interactions, this discriminating procedure can reject 99.7% of background electronic interactions, while still capturing correctly 50% of the nuclear interactions. Electronic recoil backgrounds can also be further reduced by using low radioactivity materials for all detector components, and by regularly filtering the liquid xenon to remove traces of radioactive isotopes such as tritium, krypton, and radon. Xenon can be cleaned to extreme purity levels, meaning that XenonNT contains the purest xenon on Earth. So if we want to capture dark matter WIMP interactions in a xenon detector, we have to look for an excess of nuclear recoils within the xenon tank. But how do we know these nuclear recoils are really WIMPs, and not just mundane neutron and neutrino interactions that leave a very similar nuclear recoil signal? Well, the central XenonNT detector is surrounded by a 700-ton water tank featuring active Cherenkov neutron and muon veto systems. The muon veto is the outermost part of the XenonNT experiment. If a muon flies through the water tank, it produces a cone of Cherenkov light that can be captured by photomultiplier tubes. That's the same light that produces the eerie glow when high-energy particles traverse the cooling water tanks of nuclear reactors. If a nuclear recoil is detected in the xenon tank around the same time as a Cherenkov cone is seen in the water tank, then the nuclear recoil may have been produced by a penetrating muon and is hence discarded. The neutron veto is contained inside the muon veto. Neutrons, mostly generated by radioactive impurities in the infrastructure of XenonNT, have a high probability to be captured by the hydrogen nuclei of the water molecules. A characteristic photon is emitted when neutron captures occurs and triggers photomultiplier tubes in the neutron veto system. If a nuclear recoil is detected in the xenon tank at the same time as a characteristic flash is seen in the neutron veto system, then the nuclear recoil may have been produced by a neutron and again is discarded. The active muon and neutron veto systems allow all neutrons and muons that still reach the central xenon tank 1.5 kilometers underground to be identified and discarded. and means that XenonNT can safely scour for WIMPs without fearing these interactions as backgrounds. And xenon-based experiments work brilliantly. XenonNT's predecessor, XenonNT, set a world-leading limit on the minuscule interaction rates of WIMPs with matter. However, the elusive capture of dark matter WIMP interactions still eludes direct detection experiments, and now that goal may have just become a whole lot harder. Direct detection dark matter experiments may just have become a victim of their own success. So what is this new hurdle? Well, the sharp amongst you may have noticed that I didn't explain how you can discriminate between the interactions of hypothetical dark matter WIMPs with a xenon nucleus and neutrinos with that very same nucleus. Neutrinos from the Sun can interact with the nuclei of the xenon atoms in the XenonNT tank via coherent elastic neutrino nucleus scattering, CE-NUNS. This standard model process was first predicted in 1974, but has been challenging to observe due to the very low energy nuclear recoils it produces and the elusive nature of neutrinos, which typically pass through any material put in front of them. Indeed, it took until 2017 for the coherent experiment to report the first observations of coherent elastic neutrino nucleus scattering with higher energy neutrinos from a neutron source in Oak Ridge, Tennessee. It has long been predicted that as direct detection dark matter experiments become larger and more sensitive, they would eventually be able to detect solar neutrino interactions directly. Trillions of neutrinos from the Sun stream through any Earth-based detector every second and cannot be blocked by shielding. If these solar neutrinos interact more frequently with a dark matter detector than WIMPs do, they will swamp our detector, producing an irreducible background that drowns out any dark matter interactions and potentially hides them from our view. This problem became known as the neutrino flaw, denoting a hard cutoff that direct detection dark matter experiments would likely not be able to cross. In 2009, Louis Strigari, an astrophysicist at Texas A&M University, published the first specific predictions on when detectors would reach the neutrino flaw. His work was widely discussed in 2013, turning the neutrino flaw into an active dilemma for dark matter physicists. It has been a lurking concern ever since. Now, the latest results from dark matter experiments, released just this month, suggest that direct detection dark matter experiments are performing so well that they have reached the neutrino flaw, without yet discovering those elusive WIMPs. The energy distribution of solar neutrinos can be calculated theoretically and compared to detector data. Radioactive processes in the Sun involving different elements produce neutrinos with different and specific energy distributions, which fire out into space and stream through any Earth-based dark matter detector. In those detectors, those neutrinos produce low energy nuclear recoils with characteristic energies, and our cutting-edge dark matter detectors may have just detected such recoils. On Wednesday, July 10th, at the International Dark Matter Conference in L'Aquila, Italy, the XenonNT collaboration announced the first measurement of low energy nuclear recoils consistent with being caused by solar neutrinos. XenonNT observed an excess of low energy nuclear recoil events over the expected background, compatible with a signal from solar boron-8 neutrino interactions. The signal had a statistical significance of 2.7 sigma, meaning that there's only about a 0.35% chance that the observed signal is due to background noise. The analysis used data collected over 2 years, from July 2021 to August 2023. Some may dismiss a 3 sigma result as a statistical fluke. However, the PandaX collaboration note that the PandaX detector, the particle and astrophysical xenon detector, located at the China Jinping Underground Laboratory in Sichuan, China, also detects the same interactions and ascribes them to boron solar neutrinos with a significance of 2.6 sigma. XenonNT and Panda X have become the first experiments to measure nuclear recoils from neutrinos produced in the core of the Sun. They join the list of famous solar neutrino detection experiments, most of which typically require 10 to 500 times larger detector masses. The upshot is that we can be fairly certain that we are now scraping the neutrino floor. So is reaching the neutrino floor a good or a bad thing? Because on one hand, I'm talking about extremely cool sensitivity results, but on the other, I'm kind of hinting that the ability of direct detection dark matter experiments to go any further is over. Let's look at some problems and then some positives. First, the negatives. There is now a new background that direct detection dark matter experiments must overcome. Neutrino interactions look very similar to hypothetical WIMP interactions, so it may be fiendishly difficult to separate them from one another. Teasing out any hiding WIMP interactions will require us to exquisitely understand the energy spectrum of neutrino interactions and to include them in any analysis. To map the neutrino backgrounds appropriately, experiments will likely need to be larger and run for far longer. Keeping hulking tanks of noble gases stable for years at a time is a huge technical and logistical challenge. WIMPs could still be hiding in some even more weakly interacting basement beneath the neutrino floor, but spotting them in a writhing sea of neutrino interactions will be incredibly difficult. However, reaching the neutrino floor is not all doom and gloom. There are many positives associated with the new paradigm in which dark matter physicists now find themselves. Reaching the milestone of the neutrino floor means that experiments like XenonNT have demonstrated exquisite stability, sensitivity, and the ability to separate signal from background. When boron solar neutrinos interact in xenon, the signals they produce are extremely tiny, typically only 2 scintillation photons and 5 ionized electrons. Yet XenonNT and Panda X have both been able to separate these whispers from background noise. The direct detection of solar neutrinos is incredibly difficult. Far larger detectors are usually required to study neutrinos via indirect methods. XenonNT and Panda X have opened up a new way to study neutrinos with more compact detectors. Indeed, XenonNT scientists have even suggested that the detector could be used to detect early waves of neutrinos from supernova explosions. That would allow astronomers to focus their telescopes on the later arriving photon bursts from these cosmic explosions. A fascinating possibility. Another positive is that reaching the neutrino floor indicates that direct detection dark matter experiments have covered as much of the parameter space as they can when looking for WIMPs. They have left no stone unturned. These experiments were always going to hit this limit eventually, so it's better to hit the hurdle as soon as possible, and then scientists can work on understanding and overcoming it with the next generation of dark matter experiments. So, might it be possible to burst through this neutrino floor? Well, at the end of 2023, a panel tasked with enumerating the priorities of the US particle physics community included in its report a plan to build an even bigger, next-generation dark matter experiment. And this year in May, a representative of the Department of Energy, one of the largest funders of US particle physics, announced its support for that recommendation. So it's clear that scientists now see the neutrino floor as more of a glass ceiling than a hard barrier. A glass ceiling that can be shattered. Indeed, many dark matter physicists now reject the idea of a hard neutrino floor and prefer to use the term neutrino fog to denote a murky, obfuscating hurdle that can be penetrated and overcome. Descending into this neutrino fog presents new challenges for direct detection dark matter experiments. So how can we peer through the gloom? Well, firstly, we need to understand the neutrino background precisely. If we can exquisitely map the energy distribution of neutrino interactions within a dark matter detector, it may still be possible to identify minor deviations and excesses peeping out above that background. However, mapping neutrino backgrounds appropriately will require detectors to be far larger and to run for far longer. After all, neutrinos interact very weakly. Keeping hulking tanks of noble gases stable for years at a time is a huge technological and logistical challenge. We could also develop temporal methods. Much of the work of untangling a dark matter signal from neutrino backgrounds will come during data analysis. One strategy involves taking advantage of the natural ebbs and flows in the amount of dark matter and neutrinos hitting the Earth. Dark matter's natural flux, which arises from the motion of the Sun through the Milky Way, peaks in June and reaches its lowest point in December. Solar neutrinos, on the other hand, peak in January when the Earth is closest to the Sun. So by looking at the temporal dependence of nuclear recall signals, it may be possible to tease out separate contributions from WIMPs and neutrinos. Neutrino and WIMP interactions could also be separated by so-called directional methods. At the moment, if we see a nuclear recall signal in a dark matter detector, we have very little clue about the direction the incoming particle came from. This is true for both dark matter and neutrino signals. However, if we were able to tell which direction the interacting particles were coming from, we'd be able to figure out whether or not they were more likely to be a genuine dark matter signal. This works because we expect the direction of the dark matter particles hitting any detector to be aligned with a particular direction on the sky, in the direction of the constellation Cygnus. On the other hand, if we see a signal coming from the direction of the Sun, we know that that signal was probably caused by solar neutrinos. So the development of directional technologies will ultimately be necessary to see below the neutrino floor, and to be sure that we're really detecting dark matter. The Cygnus group is currently working on developing these future directional detectors. That is the true cutting edge. Of course, it's also possible that a neutrino floor or the neutrino fog won't be an issue at all. It's possible that the neutrino floor could be a total non-issue if dark matter does not consist of WIMPs. Another potentially viable candidate for dark matter is the axion, a hypothetical particle that solves the lingering mystery of the strong nuclear force. While WIMP and neutrino nuclear interactions look very similar, axion interactions would appear very different in terms of energy and would cause mostly electronic recoils, so they'd be easy to see in a detector like XenonNT. Indeed, the predecessor to XenonNT, XenonNT, believed it may be seeing evidence of low-energy electronic recoils caused by axions in 2020. However, that signal disappeared in XenonNT. If dark matter is not a WIMP, the neutrino fog is burned away. So the neutrino fog is not the death knell for direct detection dark matter experiments that it may first appear. There is much work still to be done in this field. Direct detection dark matter experiments have reached an exquisite level of stability, sensitivity, and precision. They have left no stone unturned in the search for particulate dark matter, an elusive component of our hidden universe. However, their stellar performance now sees them run up against a new hurdle: the murky, obfuscatory blanket of the neutrino fog. If the science and funding align, it's possible that the United States could soon be looking to build 2 Generation 3 direct detection dark matter experiments, one using argon and one xenon. However, these experiments will require new technologies, new approaches, and new analysis techniques to tease out the faint signals of dark matter interactions from the oppressive neutrino gloom. When it comes to understanding the cosmos, we must not fail to reveal any corner of the fog-covered map of our universe. I want to know what you think, because you're the scholars of enlightenment that I do this for. So please take a moment, if you wish, to let me know down in the comment section. And if you like this video, please consider leaving a like, subscribing, setting up notifications, and sharing this video more widely. I can't tell you how much these simple actions help me out and how much I'd appreciate it. Thanks for watching. Thanks for being scientific. Thanks for being bad.